Okay, this is going to be a fairly quick review of the course and getting prepared for the exam. Um, so we are going to go through that, do the review of open loop and closed loop, VFDs, servos, and safety PLC logic, which will be some of the key things for the exam. So your exam will be open book. You can use whatever you want for the exam to help you, as long as it's not another person. It will be written during your regular lab time. You will all be in the room together with your regular lab group of 25 people or whatever it is. So we won't be subdivided into two separate groups like we've done for the other tests. It'll just be everybody all at one time. So if you are in Monday 2 till 5, you will be just writing at 2 o'clock on Monday. There won't be a second time to write on Monday, just everybody's at the same time. The test will be 120 minutes, so 2 hours. It should not take you that long, but that's how long you will have. There are a lot of questions, like maybe about 40 questions altogether, I think. It is multiple choice, blackboard, multiple choice, and short answer type of questions. So it'll be a lot like the assignments have been. So what are we covering? So the last couple of lectures primarily, and then some general things from the rest of the term as well. So what did we talk about in the last couple of lectures? We talked about open loop versus closed loop systems. So you might remember their open loop systems, they don't monitor or measure the state of their outputs. The example we have there is checking a thermostat versus just having a fire. A fire is basically just either on or off. That is an open loop system. You're not monitoring anything. Closed loop systems, we are actually monitoring, we're using some type of input to monitor the status and then control our output based on what that input tells us. Can be an encoder, can be some type of other measuring device. Example we might use there is a thermostat. We actually set a desired set point temperature, and then we monitor our current temperature, and then we control an output to try to achieve that set point temperature. So if we go above the temperature, we would turn our heating element off. If we are below the temperature, we turn our heating element on to try to achieve that set point temperature. We talked about different types of control methods for that as well. We talked about PID, or proportional integral derivative control, a little bit. So that's a very nice way to be able to achieve that effect. Here's a little diagram that explains that as well. You can see there we have a set point of 1, and this is adjusting the P, I, and D values to try to get a nice response of how to move your output to that desired set point without doing a big overshoot or have a long settling time either, trying to get to that set point nice and quickly without overshooting too much by adjusting the P, I, and D values. I gave the example of the pellet grill that I'm looking at, which also has PID control to control the temperature. As it says here, it's a digital PID control board to be able to control the temperature, so that actually controls how many wood pellets get pushed into the grill to try to maintain the perfect cooking temperature that you set. Some other examples here. I demonstrated this was our robot for a robot competition this year, and demonstrating here the arm that moves on this moves to a couple of different set points. and that is PID control that moves there. So we basically tell it to go to the vertical position, and it automatically controls to move to vertical. So it has encoder feedback. It tells it what its current position is, and it uses that feedback to control the position of the arm. It's one of the things that it does. We also have the ability to manually control some of the other features on here, like these climbing arms are all controlled manually. So that is an open loop system to do that. They do not have any type of encoder feedback on them. You just push a joystick and they either advance or return based on where you're pushing the joystick. It doesn't know where it is actually positioned or what position it's trying to get to. It's all just done manually. So that would be an example of open loop control. So that's open loop versus closed loop. We talked about VFDs. VFDs stand for variable frequency drives. An AC motor will always spin at a constant speed based on the frequency that is being applied to it, the frequency of the three-phase power. That is just a design feature of a three-phase motor. What we can do with a VFD is actually manipulate that frequency using pulse width modulation to try to actually control the speed or direction of that motor by manipulating what the frequency actually looks like. So there's a good video that explains that in very fine detail. So we talked about VFDs, lots of stuff there. We also talked about servo motors. Servo motors, commonly used on robots or other precise positioning or speed control applications. This is a special type of motor that allows us to control very accurately the speed. We have some type of device on there that gives us feedback, typically an encoder. That will be used for that. There's a video here that we watched in detail about that. And the other big thing that we've done in recent weeks is talked about safety PLC programming. So we got into there and started talking about why do we actually use safety PLCs. So we're basically controlling dangerous motions with the safety logic as opposed to the standard logic of the PLC. And we demonstrated how you can easily manipulate and change, whether intentionally or accidentally, standard logic. And that makes a dangerous situation if it's a function like a stop button that can be jumpered or forced or whatever in your PLC logic. So we want to have a way that we can make logic that cannot be changed or cannot be accidentally jumpered around or tampered with. And this is where our safety PLC comes in. So standard logic can be written wrong. There's lots of things that can go wrong in the process of creating standard logic. Safety logic, however, has a bunch of fail-safes built into it. So one thing we're always going to use is normally closed devices for safety devices. We're also always going to use dual channel devices. So we'll always get two signals from a safety device, and those two signals should always agree with each other so that we know that things are working properly, that nothing has failed. Safety devices we might see: e-stops, pull cords, gate switches, light curtains, and lots of other things too. Area scanners, safety mats, or enabling devices, all different things we might see on a safety system. Your safety PLC is probably going to be red, and we are probably going to control actual contactors which will physically interrupt the high voltage power going to motors or robots or other devices like that. So we have standard logic that controls our regular contactors, and then we'd have safety rated contactors which we will use in pairs. We always control outputs in pairs. So we would have regular standard conveyor contactor. We will control their standard logic. And then we will have a pair of safety contactors upstream that will break our 480 power or our high voltage power to this system as well. So our safety circuit controls this, and then our regular just turn things on and off. Standard logic would control this. We gave some examples of this in the lab. We can show how we can set up different zones for this. And then we got into the actual blocks. So we're using these redundant input blocks for all of our devices. So we did this in the lab. So we can use these for both e-stops, safety gates, and light curtains. The redundant input block. We define this as either manual or automatically resetting. We have our channel A and channel B. That's the two inputs from the actual device itself, the dual channel inputs. We have a reset. If we're going to do a manual reset, we need a safety tag to do the resetting. And then we have a fault reset as well. If this block were to actually fault out, we need a tag to do the fault reset. So we demonstrated how we can run that. We can also do a redundant output as well. The redundant output works very similar. We have a tag, we have a feedback type, which will be positive. We have an enabling tag, which is what do we actually want to, a safety tag that will actually turn this block on. And then we have a fault reset, and then we have two feedback devices as well. So when we turn this block on, this should be driving a physical contactor. And then we have signals that come back from that contactor to confirm that that contactor has actually closed. And that would be our feedback signals. And the .01 outputs from all these blocks we can use in combinational logic within the safety task of the PLC to create different zones and things like that, to do whatever we want with safety logic as well. And that is the general idea behind safety logic. Once you have completed and validated all of your safety logic, your final step, we didn't do this in the lab because it's kind of tricky and dangerous, but your final step is to create a safety signature and lock down your code. So this is where you actually create a kind of a digital fingerprint of the condition of your logic at the time where you locked it. This is like you signing off on it. So you basically assign a password. It creates a passcode that you will see, and that way no one can come in and change your safety logic after you have locked it down with a safety signature. People can monitor it, but they cannot change it unless they know the password. And that is about it for Safety PLC. And that is about it for the new content that we've done since the last test. So, exam should be this content. Know all of the assignments that you've done. Know the labs that we have done. And you should be all good to write the exam. So, good luck with the exam, and we will see you this week. Thanks.